real-time lectures. So today is lecture 13 of quantum physics for non-physicists, and today is the 27th of October. Okay, and today we will finally start with stationary states in one dimension where we have a potential that is non-zero. And for this, we'll follow very closely now chapter 15 of the Schumacher and Westmoreland book, which is a very, very nice chapter as far as I'm concerned. So we'll see first how to attack a general problem when we have some kind of potential. So we'll see what conditions we need to impose on the solutions, and then we'll see a few examples of this. And our daily analogy is also a summary of what we did in the previous lecture, in case you haven't had time to see it yet. So in the previous lecture, we consider a wave function that is bound, it's free inside a box, but outside the box, we just say it has infinite potential. And so we just say that the wave function must be zero at the borders of this box. Okay, and then the behavior of this wave function for stationary states is very much like when you have a musical instrument. I think this is some sort of banjo, and you have the strings are bound in the two extremities. So when you pluck the strings, then they can only vibrate at certain frequencies that correspond to either, like one full, like half a period, half a wavelength being the whole length of the string, or a wavelength, or something like this. But the range of frequencies at which it can vibrate, it's limited. That's why you have different lengths of the string for different frequencies and different musical notes. So it was the same in the case of the bound particle. We saw that if we fix it to be zero at the extremities, then all the momentum that are allowed for stationary states are the ones that result in having like a multiple of half a wavelength corresponding to the length of the box, right? So it could go up and down and up. So they all corresponded to functions of the sort sine of kx, where k was limited. Okay, so this is what we did last time, but now it was more like a prelude to what we'll be doing now, because some of the solutions will look a little bit like this, but I think not the ones we'll see today. It depends on how fast we go. All right, so let's see. Let us start. And let me just add here the chat so I can see what you're saying. Very good. Good. So now we have a general, finally, we have a general Hamiltonian. We have a general Hamiltonian H, which is p squared over 2 mu plus some v of x. And in case you're wondering, because p is an operator, this will also be an operator, but that's just v of x times the identity. So this v of x is a real number, so sometimes we just write v of x without the hat. Okay. So why do we look for stationary states? First, because they're easier to find, and second, because we can express general solutions, or many general solutions, in terms of a superposition of stationary states. So let me explain what I mean by this. So one, what are stationary states? As we saw a few times, they satisfy they are eigenstates of the Hamiltonian. Okay. And what this means in particular is that when you want to evolve them, if I say that psi e is the initial state, when I want to evolve it, it is given by I h t for h bar. And this is just going times my initial state. But because it's an eigenstate, then this is just going to be E minus I E of h bar t sine E. Okay. And we saw that we can call this like the frequency. So it's just a global phase that oscillates with this frequency. Okay. And so because the global phase has no physical meaning in the sense that for all the probabilities of observables that we want to compute, it will go away, then we say that the stationary state is like, almost by definition, it's the one that does not evolve under this Hamiltonian. And so first of all, they're nice to find, they're easier to find. And second, the nice thing is that if you want to do the evolution of a non-stationary state, if you can express it, for example, phi, if you can express it as a superposition with some coefficients of stationary states, then this leads to, when you do the evolution, it will just become the evolution of E. Right. Where these are easy to evolve. And then you just need to compute the superposition. Of course, now this phase is not a global phase anymore, but this becomes a relative phase. Between the different terms in the superposition, right? And we did an example of this in the previous lecture, where we started with just the particle in the box, and then we took the superposition of the first and the second stationary states, and we saw that it behaved more or less like a particle moving from the right to the left and bouncing back. Okay, it was precisely by doing this. Okay, so this is kind of the justification of why when we have a new problem, meaning a new Hamiltonian, the first thing we do is to look for what are the stationary states. Okay, so now how do we find them? So let's just write again the time independent Schrodinger equation, which is just the equation for the stationary states is just H psi E equals E psi E. This is just what we did before, it's just a definition. So now let's just replace what this H is. It's p squared 2 mu plus v of x psi E equals E psi E. Okay, we'll move this to the other side. So we get p squared over 2 mu psi E equals E minus v of x. And if I wanted to be precise, I could put the hat there, and then here we no longer need the hat. Okay. Very good. So now let's apply this to the wave function. Okay, so and let's just remember what the wave function is. So phi of x is just x psi, so that we can write psi as the integral dx psi of x x. Okay, so it's just the function that gives us the coefficients for different position eigenstates. And we saw how p acts on this, so we can write it as, oh, let me just put a box around here. Good. So then we get p squared acts as minus I h bar and the derivative to x. So we get minus h squared to mu d squared dx squared of phi e of x equals, and now this is really just e minus v of x. Okay, let's just move this to the other side just to get only the derivative on the left of x. So minus 2 mu over h bar e minus v of x. Okay, so what we have here is just a differential equation, right? Where we have here the second derivative of function equals a constant. For each x, it's a constant times the function itself. Okay. So this is just a differential equation that we try to solve. Okay, so now how do we in general attack this kind of problems? So let me give you an example for the procedure. Because this is where we remember that it's not just physics, it's not just math, it's also physics that matters here. I'll tell you what I mean in a second. So suppose that this is x, and on the vertical axis we have v of x, and let's say it behaves in a funny way, like and then it can do something strange, we don't know, and then it behaves like this. Okay. So the general procedure is we break down the line into regions that are kind of easy to treat. So for example, we could say here, let's call this here v left, v right. This is x left, x right. And this is like the strange zone, which we're going to call interaction zone. Why do we call it this? Because it's like, if my particle is feeling a potential that is varying in some way, we can think of it as it's interacting with some other system. Okay, so it feels, for example, that there is a big magnet there, and therefore it feels this different overall energy potential. Okay, a magnet or some other big atom that is nearby or something like this. But for now, we don't care about it. It's just a name. It's the interaction. So, of course, it could have many of these types, but for now, we'll focus on something like this. So the procedure is going to be, one, we find solutions for each of the region, okay? For each easy region of v of x. So we'll find a solution for the left, a solution for the right. Two, we will glue them together. In the boundaries between the regions. And this is what we're going to see next. We'll see like what are these conditions. And three, even after gluing them together. So this means something like, oh, we found that for example, we found that the wave function behaves like this, and then something like that, but we wanted these two to be together, so we discard all the solutions that don't have this continuity here. We'll see in a second what I mean exactly. but just so you get an idea. So we find a solution for this region and a solution for that region, and then we see if they fit together. We'll have some free parameters, like some coefficients that can be adjusted, and we'll find the ones that match between the regions. Good. And finally, even after doing all of this, we might still have some solutions that are unphysical, and we'll see what this means. So we'll rule out unphysical solutions. So what we'll do next now is to see what this kind of conditions are. And then we'll see some examples of solutions for some kind of easy regions like this and this. And then we'll start gluing them together depending on how much time we have. Okay. So first of all, what are the continuity solutions? Continuity conditions. Let's just pick up our differential equation that we got. Copy. Okay. Good. So, first of all, in general, we want that any wave function is continuous. And again, this is something we impose from the physics part. Why? Because we want that the probability density behaves like a probability density. So we want that for any x1 and x2, this, which is like the probability of finding the particle in this interval, okay, this is the probability of finding the particle integral between B1 and B2. We want this for any x1 and x2 to behave like a probability density. So essentially like a probability distribution. And this means it should not have like sudden jumps in particular. Okay, now this is it's still relatively hand-wavy, but for now, let's just accept that this is what we want, and we consider solutions where the wave function is not continuous to be unphysical for now. What about the first derivative of x? So z dash, z prime is just this. Well, this one is continuous if v of x is finite. And why? Well, we can just take this. We take this this differential equation and we integrate it once to find the derivative. So by the way, this is just for the energy eigenstate, whereas the other one is general. So if you just integrate it once around some point x0, then we get not plus because it's a minus 2 mu h bar square. And now the integral of E minus v of x. This thing, right? So I just took this differential equation and then I integrated around little x0. But if this potential is finite, then this is just a number. Okay, sorry, and here's from x0 to x. And I'm missing the dx. And this one here is continuous. Okay, so overall, this is going to be continuous. So an exception to this is when the potential is not finite. So for example, in this particle in a box that we saw where this wall suddenly become infinite, there the first derivative is not going to be continuous at the edges of the box. What about the second derivative? So this is the second derivative of the stationary state wave function. Well, this is continuous if v of x is continuous too. And why? Well, we can just take, because we can just take the actual wave function. Oh, sorry, differential equation. This is continuous. This is what we're looking for. And if this is continuous, then it's just a continuous function times a continuous function is going to be continuous. Okay. So again, what's an exception for this? When will the second derivative not be continuous? When we have, for example, a box, when we have a step potential. Yes, when the potential goes check, 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 for example. Then the second derivative is not continuous. Good. Now, these are all conditions that we'll use when we have solutions for the stationary states in different regions. And then we need to see which ones are compatible with like the gluing together of these different regions. But there's a few more physical conditions that we will ask for. So other physical conditions. So the first one is going to be that the wave function is normalized. What I mean is that, like we saw, if we integrate the wave function from minus infinity to plus infinity, the modular square of the wave function, this should be 1. And what this means in particular is that sometimes this differential equation will have several solutions, but some of which will diverge at infinity, like an exponential that diverges at infinity. And because this we cannot normalize, then the solution is not accepted as a physical solution. Okay, so no diversion solutions. And the other thing we'll to justify now is what's going to be, there's a condition on the energy overall, which is going to be, is larger than the minimum of the potential. So this is minimum overall x of v of x. And why this? So let's see why. Because let's see what is the average energy. Well, this is just the wave function, h wave function. Let's split this thing. So you have 1 over 2 mu jack p squared jack plus v of x, check. But now the p square, it's always going to give larger than 0 energy. Remember, this is the kinetic energy term, so it's always going to be larger than 0. So we have that the energy must be larger than the potential energy overall. So check v of x, check. But what is this? Well, we can expand it in the momentum basis. So this is the x. It's going to be v of x square. I mean, you can do all the steps if you want. Just expand each state in the position basis to get the wave function representation, etc. And you'll get here. Well, but this, by definition of V min, this is larger than of replacing here this potential with just V min. But now this is just a constant, so it can come out. And what stays inside is just the normalization condition for the wave function. So we know that that's 1. So that's V min. Okay. So this means that we will discard all the solutions that that don't have energy larger than the minimum of the potential. Okay. And of course, first we go to each region, and there it could be, the energy could be smaller than the potential in this region. But overall, when we have like the overall solution, then we need to compute the average energy of all regions, and then it should satisfy this condition. Okay. And the book has a nice exploration of this concept if you want to have a look at it, but we will not get into more details than this. Okay, let's copy again our Schrödinger equation. And now let's think about only problems that have this bounded interaction zone. So let's just get everything we need. Right here. Okay, very good. So we will treat first these zones of constant potential. We'll see what can happen in these zones, and then we'll see a few different cases. Okay, so let's first see. And the main idea, so we'll make a break soon, but let me just tell you what the main idea is. So this is a second degree differential equation where here you have a constant. So second derivative equals a constant times times the function itself. So depending on the sign of this constant, you'll get a solution that is either exponential of a complex number or exponential of a real number. That's the main idea. Okay, so depending on whether the energy is larger than the potential here or here, we get solutions that correspond to oscillating waves or that correspond to exponentials decaying. So I think we will make a break here because we anyway have like 3 minutes to make up for. So we'll continue now at 10:45. Okay, good. So we continue, and we're trying to see what happens here in these zones that have constant potential. Just chat. There you go. Okay, which means that we're thinking of zones where we have, again, v of x equals some v0. So it's going to be, for example, the one on the left and the one on the right. So then we have two options. Option one, e is going to be larger than v0. So then what we have here is that chook square of v of x minus some constant, and this constant is positive. Say of x. Okay, and the solution to this kind of differential equation is a sum of waves going to the left and to the right, where k is going to be square root of essentially this constant, h bar square e minus v0. Okay. Okay. Now, on the other hand, if we have a region where E is smaller than V0, then here we have the same. Well, let me just, oh, sorry, I forgot an I here. IKX. Good. So if we have this region, then it's very, very similar. And you can try to plug in the solution there and see that it works. So now we have here plus a constant. So what's the thing that when you take the second derivative, you get a constant, positive constant, then you need to have here tac. And just because we'll have many solutions of this kind, let's just call this here C and D. And here you have V0 minus E. Okay, otherwise it's the same. So, this is the kind of solution for energy larger than your potential, and below is a solution for energy lower than your potential. So it's the difference between having a superposition of waves, one wave moving this way and a wave moving that way, or having the superposition of an exponential going down and the exponential going up. Okay. And now, depending on the exact setting, we will set these different constants A, B, C, D to be different things. So that's how we generally approach this kind of problem. So now let's see different cases. Case one, what is called the reflecting state. And this is the case where V on the left is smaller than the energy of the eigenstate, and V on the right is larger. Okay. So again, x, V of x, we have something here smaller than, let's make it even smaller. Chook. Then something happens here. Ooh, we don't know what. And then there we go. So this is VL, this is V right. And this here is the interaction zone. we don't care about for now. Okay. Then what did we learn? So we learned that on the left, we're going to have solutions of the sort of a wave going in this direction and a wave going in that direction. And so far they seem both to be allowed. So let me just write here what we have. So this would be A, sorry, this one is A, E, I, K of the left, X, that's the lower one, and this is B, E minus I, K left, X, right? So that's the one going to the left. Where here on the right, we could have something like this and something like that. So this would be C, E2 minus B on the right, X, yeah. Okay, we can call this this exponent here B, just to be the same as the book. Okay, B and minus B, and let's just call this B here. Okay. Just because it's not an oscillating thing, so don't call it K. Okay, and this would be D, E2 minus plus PR X. Well, if this potential continues like this all the way to infinity, right, then we do not want to accept this solution because it would diverge. So we have right away that D equals 0. There's also a relation between A, B, and C, which we can deduce, but for this we need a bit more material. So we'll see this in the next lecture. But overall, what we know about the wave function is, so, well, it's going to be some A, E minus I, K left X plus B, E I, K left X, if X is smaller than XL, XL, X, right? It's going to be C, E minus B, R, X, if X is larger than XL, and it's going to be something else that we don't know yet. It will depend on the actual potential between XL and X, right? Okay. So that's the general solution. And we'll leave it at this for now, okay? And then later on, we'll see that, for example, A square needs to be the same as B squared. But these are details we'll leave for the next lecture. Okay, but indeed, we can know a lot already about A, B, and C. So about the wave function, how it behaves asymptotically, even if you don't know the details of the interaction zone. Good. So let's see another case. Scattering states. So these are the case. Let's write it here, where both VL and V right are smaller than E. Okay, so this would be corresponding to a case like that goes X, and V of X looks like something like Zurich. Something happened, we don't know. Something crazy, but then Zurich. And let me just write what the energy is overall. So let's suppose that here's E. Okay, like in this case, let's say that here is E. So the energy is above both cases, above the potential on the left and on the right. So then we have solutions of this form. Oh, let me just write here the box boundary. This is the interaction zone, check, check. So I have solutions here of this form, and here again we have solutions of the same form, like going one way and going the other way. Okay, so we have A e to the I kx x b e minus I k, sorry, k left x, k left x, and here we have c e I k right x d e I k left x. So this is a general solution. It would be something like this, but we can see it because what we have in the wave function is like a superposition of this term d and c, the same on the left, but it's kind of convenient to look at it as a superposition of two different cases. So let me just write here. Of the case where this particle is only outgoing on the right, and the case where the particle is only ingoing. We didn't do anything. We just said, well, we have the total wave function being this thing, and we can break it down as a sum of these just situations. And why we do this is because it's easier to think physically about what each of the situations looks like. Okay. So now we're going to look at this first case here. And now let's make like a classical approximation. Let's think, just to think for ourselves, like this is really a particle that is coming here. It finds some funny potential, and then, well, part of it gets reflected back and part of it gets transmitted. So this is the general idea. And here we have the same, but from the other direction. Okay. So now we look at this kind of solution. So look at solutions where d equals 0, just because we want to consider this scenario. Of course, to get the general solution, we'd have also the one where c is 0 and d is not 0 and sum them up. But it's just nice to think of this case. Okay. So then we have the solution. Phi of x being a to I k left of x plus b e minus I k left of x if x is smaller than x right, and c e plus I k right of x. This should be here and L. Right, and something in between. Okay. Good. Okay. And this is what is considered scattering, because we think of the particle incoming, part of it getting transmitted, part of it getting reflected. And this could be something like the particle finds something like we said before, like an atom in its way. Good. And then from this, we can determine, and this is useful in several experimental settings, some coefficients that are relevant. So I'll write them in blue, which are the transmission, coefficient, and the reflection. Okay, where's this is going to be T, K right, C squared over K left, A squared, and R is going to be, well, K left. It's going to tell us like how much of the wave goes to the of the incoming wave. If you think of the part with A as being the incoming wave, how much of it will get transmitted versus how much of it gets reflected. Okay. And this will be useful later on when we consider just also non-stationary states. And it will be the case that T plus R equals 1, and this comes just from normalization of the wave function. We will see more into the values of, into the interpretation of this in the next lecture of these coefficients. Okay. Good. Now there's only one more case missing. So we saw the case where the energy is higher on the left but lower on the right. The case where it's higher on both sides we're missing the case where it's lower in both sides. Okay, these are number 3. Bound states. And these are the ones. X, p of x. And here is like the average energy of the particle, and it's going to be something like this. And it's going to do something. And it's always going to be, this is a bad example. In fact, this is an example that would not be allowed. And why? Because here it looks like, if I'm honest with the way I drew these lines, it looks like the energy is even smaller than the minimum of energy. And we saw before that, the minimum of the potential, and we saw before that this is not allowed. So we need to change something here. Yep. In this drawing, let's say something like this. Okay. There we go. So in this case, as we saw before, there were a few types of solutions. So there was this and this on this side, and here on this side again, this and this. Right. I forgot to draw the box, but let's draw the box here. Check. Okay. So here we'd have, no. We have here A, E, B, X, B, E minus Bx, and this is B of the left. C, E, and dE minus bx. Okay. And just like we saw before, there's a few cases that are not physical here because they'll diverge at infinity. That'll be this and this one. Right. So we need to have only this kind of cases. And instead of D, we may as well call this B because B is a letter that is not free. So we have that the wave function is equal to A e to be x for x more than x left. Interesting that this disappeared. X left, x right. And be minus bx for x larger than x right and something in between. Okay. Good. And like we saw, in order for there to be like a wave at all, a particle at all existing here, then we need this potential to go below the average energy at some point. Otherwise, we don't satisfy this condition that we saw before, the physical condition. So this U minim here, sorry, V min, this is going to give us a boundary condition for the different energy eigenstates. Good. So this was just like a very broad overview over the three different types of solutions that we can have where we have just one interaction zone in between. And now we want to slowly build up to simple cases. So now our goal, as we saw before, is to treat some specific cases like the potential going like this, or so there's a step potential, box, which is a potential going like so, or even something like a scattering barrier, which is the opposite of a box. It's just check, check, check. Okay. So now we're going to see each of these cases in more detail. Very good. So this is in more detail. And let's start first with number one, this potential step. By the way, you'll do the box in the exercise class. So on Thursday, we will just get an overview of it. So now we want, x, v of x, and we want this to go like chook, chook, chook. Okay, so now we don't have this interaction zone being some complicated thing that we don't know. We know exactly what it is. Okay, and this is, let's say this is x equals 0 for simplicity. Okay, and let's say that the average energy is somewhere in between. Yeah. And let's say that this here, let's call this 0, and let's call this here V0. Okay. So this is V on the right, and this is V on the left. So now we get to this part. So if we look at what we did in the beginning, we said that the general procedure was going to be to find solutions for each easy region. And now we need to glue them together in the boundaries. So that's what we're going to do. Okay. So by the way, we saw that whenever the potential is not continuous, which here it is not, so we have v of x equals 0 for x smaller than 0, and v0 for x larger than 0. We have a discontinuity point, so we know that the second derivative of the wave function is not going to be continuous at this point. But the first derivative is still going to be continuous because the potential is finite. Okay. So we have the general solution. So by the way, this is the case of reflecting state, which means that E is smaller than E0. So we're going to expect something like here's superposition of it going one way or the other, and here's somehow it decaying. Okay. So in this case, what we know, well, we have so x equals a e I kx plus b e minus kx for x smaller than 0, and c e minus b x for x larger than 0. Okay, so we are going to take, you remember that we can always, from here, from this a and the b, we can always like factor the global phase out. And then we have some freedom, like the way we depend the way we choose the absolute value of a will give us the absolute value of b and c. So we're going to take, we'll see this in more detail next lecture, but for now we're going to take this a to be 1. Okay, so that we have just fewer constants to care about. Okay. And what are the values of k and b? We can just repeat what we had before. So for k, we had square root of 2 mu over h bar squared, and here was e minus v in this region, that's just e, and b is square root of 2 mu h bar, and here's this v0 minus e. Okay, so now we apply the continuity conditions at the only point that is critical, so it's going to be this x equals 0. So we want that psi of x is continuous. So this means that, well, 1 times e I k times 0 plus b e minus k times 0 equals, so the wave function coming from the left is equal to this wave function coming from the right. There's an I missing here, minus b times 0. Okay. So that's 1, that's 1, that's 1. So we get this condition that 1 plus b equals c. Very good. What else do we have? Let me just make a bit more space. We saw that here the first derivative is also continuous. Right? So let's take the first derivative on the left. So we get ik times eik. 0 is the x value, plus, well, we get a minus b ik 0 equals little b c e minus b 0, right? We just did the first derivative, and then we replaced x by 0. So this is, this is 1, this is 1, this is 1. So what we get, we have that I times k, and now we have b, 1 minus b, 1 minus b times ik. This equals bc. Okay, and now we have two linear equations for two variables. The only variables are large b and large c with two equations, so it means we have already determined them. Okay, so solutions. With this, and you can do it yourself to convince yourself that this is the case, but you get k plus b, ik minus b, and c is going to be 2ik over ik minus b. Yep. And one nice thing is that, yeah, this b squared is 1. Okay. And in fact, we can now simplify them further by replacing the k and the b from these values here. And we can obtain the final solution, which is not super pretty, but it is I square root e plus square root of v0 minus e over I square root e minus square root v0 minus e. And here we have 2I square root of e and I square root of e minus v0 minus e. Okay. So what can we take from here? Well, first of all, these coefficients of like how much gets reflected, how much gets transmitted, they depend on the relationship between the energy and V0. And you can think of the case V0 being much, much larger than E. So this is the case where this barrier here is very, very, very high. So it goes there. Then, of course, we expect that it's very hard for the particle to go through this very high barrier. So this thing here is going to go to 0. So C is going to go to 0. Okay. Then, yeah, C squared is going to be much smaller than 1. Okay, so which means that it's going to be very hard to find the particle on the right. And the further we get away from it, so the further we get away from x0, the further we get away here, if we want to find the probability of finding the particle there, it's going to depend on C squared and E2 minus bx. Sorry, let's just say, what's the probability of finding the particle at some x that's much larger than xr? Then this is just going to be given by this squared, which in this case is going to be c squared and d2 minus 2bx, right? Which decays exponentially. Okay. Very good. So what was the other case we didn't see? We also want to see now a potential step, but where the average energy is larger. So how do I do this? We just put E here. And I'll take it up. Okay. So now we know that we have a scattering case. So we know that the solution on the right is also going to be chuk, 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 plus the other term that goes back, right? But now we consider only the ones of this term that goes to the right. Okay. So let's attack this. What do we expect? Well, we expect there to be overall more density of wave function on the left than there is on the right. So we do again the same calculation. So for this case, phi of x, and we know that the real solution is superposition of this and the other one. But we have I k x. We set again a to be 0, to be 1, sorry, plus b e minus I k x for x smaller than 0. E c times z I k right x for x larger than 0. And again, we have our case being given by those things we saw. Chuk. Oh, yeah. Copy. We put it, let's make some room here. This was the reflecting case, and this is the scattering case, which means E larger than V0. Then, so we have, K is this, K left is this, and K right is this, but wait here. We saw that E is larger than V0. E minus V0. Okay. Very good. So then we do again these conditions that psi of x and psi prime of x must be continuous. So we'll do psi of x continuous gives us exactly the same thing as before. Can do it. 1 plus b must be equals to c. And psi prime of x being continuous. Now we have an I also on the right, but the solution overall is going to be I. Okay, and now here 1 minus b that comes from the left. It's going to be I, k right, left, c. And then the solutions. Again, we have now two linear equations for two variables. So the solutions are going to be that b is k left minus k right over k left plus k right. Compare this to before. Before that was here ik left and c is going to be 2k left over k left plus k right. And now we can again express them in terms of the using these things here. And I'll show you the solution because it's straightforward, but not too interesting. Replacements, we have e minus v0 root of v plus e plus v0. And here we have 2 square root of v, just because all the other terms with the h bar and the mu cancel out. E plus square root of e minus v0. Oh, and here should be a minus. Right. So all of these are real numbers now. And good. Okay. And then we might analyze this in more detail in the next lecture. We should finish here because we still have like 2 more minutes to make up for, so we'll finish there. So in the next lecture, we look at the, so in the tutorial, you will look at the case of the, we'll look at this case of the box, and we will look at the case of the opposite of the scattering barrier, the scattering square barrier, and then we'll look into a bit more detail into these relationships between A, B, and C. But for now, we already saw how to glue them together when we know what's happening in the interaction zone. Okay. Very good. So we will finish here and we will see you again on Thursday, hopefully at the right time. Thank you.